Here, Solutions Quiz 8. We're doing hypothesis testing. I claim that in the NBA playoff, fouls are called at a different key here that tells us we're doing a two-tailed test. In all NBA games, I'm talking about the proportion here, there's an average of 40. Population average, we used to use mu for. We want mu to represent something else here, so we'll use mu naught. In a sample of 36 playoff games, that's our sample size, so we use n. 41.95 sample average, we'll use x bar. Fouls were called per game with the standard deviation of 7.4 fouls per game. Note that that standard deviation is just talking about these 36 games in the sample, so this is S, not sigma. It's the sample standard deviation. That's important. And then we want 90% confidence, so that tells us that alpha is equal to 0.10, 1 minus the level of confidence. Okay, so first we're going to do the p-value method here. We want to state the null and alternative hypotheses. Sure, the null hypothesis and the alternative hypothesis. The alternative hypothesis is our claim. It's going to be in terms of mu. And in this case, since it says a different rate, it's a two-tailed test. It says mu does not equal mu naught, which is 40. And our null hypothesis is always that mu equals mu naught, so it's mu equals 40. And I'm going to write down here parenthetically that this is a two-tailed test. Easy enough. State the shape, center, and spread. For the distribution under the assumption that the null hypothesis is correct. All right, the shape is approximately normal. It's always approximately normal in this class. The reason it's approximately normal in this example is because n is greater than or equal to 30. Value for n, I think it was 36, if I remember right. Yeah, 36 was our sample size, which is more than 30. We use the central limit theorem. It gives us the shape of the sampling distribution as approximately normal. The center, we're going to use mu naught for the center because we assume the null hypothesis is correct, and the null hypothesis says that mu equals mu naught. So our center is mu naught, which is 40. And our spread, sigma sub x bar, is sigma divided by the square root of n. Both of those were things. Nope, that's not true. We don't have a sigma. It can't be sigma over root n. It's s over root n. S is our sample standard deviation. And both of those things were given to us in the problem. S is 7.4. And n is 36. Does that work out nicely? Not too nicely, I don't think. 1 point something. We could do 7.4 divided by 6, the square root of 36. And you get this 1.23 thing. All right, sketch a distribution under the assumption that the null hypothesis is correct, showing the test statistic and the p-value. Oh, kind of missed that one there. Try again. Not bad. So there's my distribution. Note it's approximately normal, and note that the center is 40, which has a z-score of 0. And what I want to do is go over here and do my hypothesis testing. So I go over to tests, and I choose t-test. It's important we use a t-test because we don't know sigma, the population standard deviation. We have to estimate it. We have statistics about the data. Mu naught was given to us in the problem as 40. X bar was something close to that, 41.95. S, note not sigma, but S is 7.4. We're not giving it the spread here, we're giving it 7.4. The calculator will figure out the spread, which it will use. And n is 36. Our alternative hypothesis is that mu does not equal mu naught, so we want to select this first one. And then you can either do calculate or draw. I'll do calculate, whatever. Either way, it's going to give you all the information you need, specifically that our test statistic is 1.58, so somewhere out here. That 1.58 corresponds with 41.95 fouls per game. And the area above that point is 0.123, our p-value. So what I can do is I can shade in this region. And, oh, that's not true. This is a two-tailed test. So I have to have a p-value on both sides. I have to also have a value over here at negative 1.58 because the p-value tells me the probability of getting a result that extreme. So it kind of be in either directions. I just said that the amount of fouls are different in the playoffs. So there could be a lot more or a lot less. So the picture should look like this. And the p-value is both of these areas combined, which in this case is equal to 0.123. Sketch a distribution showing the test statistic and the p-value. Looks like I'm good. Draw your conclusion. Because the p-value is greater than alpha, p-value is 0.123, alpha is 0.10. There is not sufficient evidence to reject the null hypothesis. So I'm not saying that the null hypothesis is correct. I'm just saying there's not enough info to say that it's incorrect. Because the p-value is greater than alpha, there is not sufficient evidence to reject the null hypothesis. That's the end of this test. Move on to the second problem. Now we're still talking about basketball. I claim that home court advantage is more important. That's key. We're going to be doing a one-tailed test here. In all NBA games, okay, so we're talking about the population here. The home team wins 58.67% of the time. Okay, 0.5867. Oh, I guess I don't have to write the number again. That is equal to P naught. Kind of think you should use P for the population proportion, but we'll use P for something else, so we'll use P naught. And we have a sample of 64 games. That's our value of N. And in those games, the home team won 41 of them. So P hat is 41 over 64. I could figure that out. 41 divided by 64 is about 0.641. Test my claim that the home team wins a higher percentage of games during the playoffs with 95% confidence. So finally, this tells me that alpha is 0.05. And now I have all the information I need to go through this test. Nolan alternative hypothesis. The alternative hypothesis is my claim. It's that P, let's see, I'm saying a higher percentage. So it'll be P is greater than P naught, is 0.5867. And my null hypothesis is always going to be that P equals P naught, so P equals 0.5867. So this right here is a right-tailed test. State the shape, center, spread to try to tie it into problems we did earlier in this class. Sure, I can do that. Shape is approximately normal. Ooh, is that going to be true? I hope that's true. Well, let's see. To figure out if it's approximately normal, you do 64 times P naught, the 0.5867, times 1 minus P naught. And if that is greater than 10, I hope it is, or I'll have to redo this problem. Yes, it is. Good. Okay, the shape is approximately normal. And the reason it's approximately normal is our criteria when we're talking about proportions is that N times P, we don't know P, but we assume P equals P naught, times 1 minus P, again, assume it equals P naught, is 15.5, which is greater than or equal to 10, so we're good. Center, P is the center, but we assume P equals P naught, which is the 0.5867. So our center is given by our value of P naught, 0.5867. And the spread, sigma sub P hat, we got a formula for that. It's the square root of, it'd be nice to use P, but we don't know P. Fortunately, we're assuming P is equal to P naught. So I can put P naught in the formula here. And if I plug that into my calculator, I'll just start over. The square root of 0.5867 times 1 minus 0.5867 divided by 64. Make sure I got the order of operations, everything right in there. That looks good. I get this value of 0.06-ish, 0.061 or 6.1%. All right, got my shape, center, spread. Now I can sketch a distribution. The picture you draw depends on what method we're doing. We're doing classical hypothesis testing here, so we want to set up our rejection regions. In this case, it's a right-tailed test, so there's just one rejection region, and its area is always alpha, which in this case is 0.05. So what I want is some region out here, so that shaded area is 0.05. And the way you can figure that out, well, okay, I should be a little bit more careful with my picture. The center, I want 0.5867, which has a z-score of 0. And then to figure out the critical value here that has 5% above it, you might just remember that's 1.645. If you don't remember that, you can get that by using the inverse norm function on your calculator. So go to distribution, and then inverse norm, tell it the area below, and then the mean and the standard deviation. You don't have to put in that 0 and 1, I'm just doing it to emphasize, and you get the 1.645. So that's what's called our critical value, and then what we got to do is find our test statistic and see if it's in this rejection region. The way you do that is stat tests. We want to do a 1PropZ test because we're talking about proportions here. P naught is 0.5867. X, which is the top of this fraction here, is 41. N is 64. And my alternative hypothesis is that P is greater than P naught. That's what this says right here. And now if I go down to calculate, I get a test statistic of 0.876. And 0.876, maybe I need to switch colors, is not in the rejection region. It's not bigger than this 1.645. My P hat, this 0.641, corresponds with a z-score of 0.876. Those guys are right here. So what my conclusion is because my test statistic which was 0.876 is not in the rejection region, there is not sufficient evidence to reject the null hypothesis. This is hard to write while you're waiting for it to write. There is not sufficient evidence to reject the null hypothesis. Good enough. So I'm not saying the null hypothesis is correct. I'm just saying there's not enough evidence to conclude that it's incorrect. That's my conclusion. There's my picture. That's the end of this classical hypothesis testing, and so it's the end of this quiz.